Okay, so now we begin chapter 5 for the centers of mass. Okay, all right, guys. So over here, the first thing that we are going to learn is we are going to use calculus. Okay, we are going to learn how to use calculus to find the center of mass of a lamina. Okay, so basically by in the M2, okay, so in the M2 book, you have learned how to find the center of mass by using these two particular formula, right? Sigma MIXI equals to the center of mass X bar into total mass, right? So I think you might be familiar with these equations. Sigma MIXI means you multiply the individual mass with each individual center of mass and you take the product and you take the sum of it, right? Because you, in M2, you used to have many objects, right? So you used to have many objects, and then we used to take the mass of each object along with its distance from the origin, and then we multiplied. We took the product. I mean, we took the sum of the products, uh, and then we equal to the x bar. We make it equal to x bar times the total mass. Okay. Okay. So, but basically in M2, all the bodies that we were dealing with, they were uniform and they were shapes that we are familiar, right? So you had a triangular lamina, you had the rectangular lamina, you had the circular arc. So those were some standard shapes, right? But now in M3, we are going to learn how to find the center of mass of not so standard shapes. So basically over here you can see, for example, they have created they have created a lamina by taking the area under the curve. Can you see over here? For example, over here you have the area. I mean, they have taken the area from the point A to the point B. So from point A to point B, you can get, I mean, you can see that there is a lamina that's created here. So basically, I want to find the center of mass of this particular lamina. So this is not belonging to any of our usual laminas. Like it's not a rectangle, not a circle, it's not a triangle, right? So the normal rules in M2 don't apply here. So we are going to learn a new method. Basically, we are going to learn how to use integration, how to use these calculus techniques to find the center of mass of this particular lamina. All right, so now let's see how we can find, how we can generate the center of mass of this particular lamina. Okay. Okay, so they say here, what we do here is they say consider the lamina as made up of small rectangular strips. Okay, so guys, what we do here is in M3, we use this special technique. The special technique using calculus is what we, by that, what they mean is they take this particular lamina, okay, and they divide this into tiny, I mean, like, you divide this into strips, like basically you cut it off into strips so small. The strips are so small, so the strips are actually so small, so that what? So what's the advantage of cutting it into really, small strips? What's the advantage of cutting? Now over here, you can see if you consider the whole shape, I mean, you don't have a proper name to this shape. But if you cut it so small, guys, what do you get here? Okay, what happens is we create small rectangular strips. Can you see? Okay, so we are going to create small rectangular strips. So for example, they have taken one such strip and they have enlarged it and shown it to you. So basically, we divide this into millions of tiny strips. So small. And so what I have done here is that small strip, I have kind of like taken it and enlarged it. Okay. So consider the lamina as made up of small rectangular strips such as PQRS, where PQ is parallel to the x-axis. Let P have coordinates xy. Okay, so over here, we will say P has the coordinate xy. Is that okay, guys? And let the width of the strip be delta x. So what do you mean by delta x? Delta x means it's so small. It's really a small change because the strip is, I mean, the strip is so tiny, right? You make it up of small rectangular strips. So delta x means a very slight change in x. So over here, we have drawn an enlarged version of it, but the strip is actually small, so that the change of x value is really small. That's why it's called delta x. Is that okay, guys? Okay, so now what we are going to do here is we are going to use the M2 technique. So what's the M2 technique? Sigma mi xi equals to total mass times x bar. Total mass means you add all the masses, right? X bar times sigma mi. So basically here the sigma mi is the total mass. Okay, capital N. All right, so guys, what I want to do here, okay, what I want to do here is to calculate the x bar. Okay, first we'll find x bar, then we'll focus on y bar. Okay, so you guys can see this is not a, this is not a symmetrical shape. Of you, if you guys can remember in M2, you remember if there is a line of symmetry, always in a shape, if there is a line of symmetry, the center of mass definitely lies on the line of symmetry. So that helps you to reduce finding one coordinate. But over here, you can see this particular shape, there is no line of symmetry. So basically, if you are trying to find the center of mass, the G, okay, I don't know where G is. So G should be, you'll have to find both the X and the Y coordinate. Okay, so both X and Y coordinate needs to be found. Okay, so if G is somewhere over here, you need to find the X bar distance and you need to find the Y bar distance. Okay, and that's our goal here. Okay, so our goal is to find the X bar, Y bar for this particular lamina. Okay, so what we do here is, as I told you, we divide this into, thousands or millions of, small rectangular strips. And what we do is, guys, y'all know how to find the center of mass of a rectangle, right? So the rectangle center of mass is something that we learned in M2. So in a rectangular object, the center of mass is exactly in the middle, right? The center of mass of the rectangular lamina is exactly in the middle. So shall we first get the mass of a rectangle and get the center of mass of a rectangle? Okay, so guys, if you remember again in M2, what we did was before going for the mass, first, how did we get the mass? We know that the mass is proportional to the area, right? Do you recall? The mass is directly proportional to the area of the particular object. So over here, first what we'll do is let's find the area. Okay, first we'll get the area of PQRS. Okay, so how do you get the area of a rectangle? Length into breadth. So what's the length and breadth here? So guys, here length means let's take the height here. So you can see height of the rectangle is the y coordinate, isn't it? Height of the rectangle is the y coordinate and breadth is delta x. Are you with me? I'm considering the PQRS rectangle. The height of the rectangle is y, breadth is delta x. So basically the area is y times delta x. All right. Okay, now let's get the mass of PQRS. So how do you get the mass of the rectangle? You guys know that all we had to do is, so in M2, you multiply it by, we need to multiply it by a simple constant, right? So let's say mass per unit area is rho. Okay, so let rho be the mass per unit area. Okay, so if the mass per unit area is rho, and if you have y times delta x times of area, then to get the mass, you have to take y delta x and multiply it by rho. Do you agree? All right. All right. So guys, in order to use this equation, you need to know the individual mass of each object. Also, what must you know? You must also know the individual center of mass. You need to know the individual center of mass of the object as well. So what about the center of mass? I need the center of mass of my rectangle PQRS. So guys, PQRS is one general rectangle. I hope you guys can see that I am marking all these coordinates and the areas in a general way, right? So that it can represent any rectangle here. Basically, any rectangle, there are like thousands or millions of rectangles here. And any one of these rectangles can be represented by this, right? Because y is not a constant. Y is a changing factor. So rectangle, the y, the height will change. All right, guys. So delta x is only a very slight change in x. Okay. And so basically this over here, this can represent the area mass of any of these tiny rectangles. Okay. Okay. So how do I get the center of mass again? So we consider our general rectangle PQRS. This is one of the rectangles. So we take this and normally you guys know the center of mass of a rectangle is exactly in the middle of the rectangle, right? So how do we get the x and y coordinate? So basically the x coordinate would be, you guys can see until this point, the x distance. Now you guys can see at S, Okay, P and S are at the same horizontal level. Now I have said at P the x coordinate is x, right? Which means at S the x coordinate is x. Are you with me? Because over here at the top I have marked P. P is vertically above S, and P has the x coordinate marked as x, simply as x. Which means we have taken x to be this, right? This distance is x. Is that okay, guys? And the S to R distance is delta x. So guys, if I want the distance of the center of mass, the x distance of the center of mass, what do I need to do? How do I get the distance from O to the middle of the rectangle? So from O to S, I have a distance x, and from S to the center of mass, guys, can you see it's half of the delta x? Can you see? So it's x plus half of the delta x, right? So it would be x plus half of delta x. Guys, can you see that? So x distance plus delta x, from the delta x, then we take half of it. So that gives me the distance from the origin to the middle, the x distance from the origin to the middle of the rectangle. All right, guys. Okay, so I want you to understand a simple thing here. Now you guys know delta x is actually what? Is a really tiny or extremely small change in x, right? An extremely small value, a small change in x, and you divide it by 2, making it even smaller. So what do you think happens when you add a really small number to x? So is it going to make a significant change to x? You know, delta x is something that we wish to do. We wish to make delta x big or as small as possible in order to make these strips, in order to make them better rectangles. Guys, you all can see we have a curve shape at the top. So in order to make our rectangles better, we need to make delta x as what? As close to 0 as possible, right? Do you guys agree? We need to, in order to make our rectangles better, in order to do this properly, delta x needs to be as close as possible to 0 as possible, right? So it needs to be as small as possible. And when you divide it by 2, it gets even small. And when you add such a number, you know, with so many 10 zeros, and you add it to a number like 5, do you think it's, for example, a value like 5, you add a number with 10 zeros, 0.000005, something like that. If you add it, do you think that it makes a significant change to this person? No, right? I think you guys can see our whole point here is we try to make our delta x as small as possible, as close as possible to 0. So to make this a really small rectangle, okay? So to make it as tiny as possible. Therefore, the center of mass x coordinate is going to be x. This is what you need to understand. The center of mass x coordinate is going to be x. The y coordinate, of course, we don't have issues. So you can see the height of the rectangle is simply y, right? The height of the rectangle is simply y here. You guys can see it, right? The height of the rectangle is simply y. So center of mass is exactly in the middle, which is half of y. So it's y over 2. So guys, this is the center of mass coordinates, and it's really important that you are able to generate them. All right, guys, so everything is ready now. So now we have to use our M2 equation. So what's the equation? You multiply the mass of each rectangle with its own center of mass, and you take the sum of all the rectangles, right? So let's take the rectangle that we know. So the first rectangle, or any rectangle basically, has a mass of y delta x times rho. Okay, multiply. So I'm going to find the x coordinate first. Okay, so we'll go focus with one coordinate. I'm going to find x bar first. So I'll multiply with the x coordinate. The center of mass x coordinate is x. Can you guys see? So I use this value here. Okay, and I use the mass here. So mass multiplied by center of mass, right? And guys, you can see now this is just one rectangle, but I'm supposed to do this for all the rectangles. I need to add this mass into the product. I need to get the addition of the products of mass into center of mass of all these rectangles. So how do I get that? So this is the general mass into center of mass product for one rectangle. So get it for everyone. So everyone starting from where? The rectangle start from x equal a, ends at x equal b. Starting from a to b. Right, guys? This is equal to total mass. Okay, or this is equal, let's write here first x bar times total mass. So x bar is the center of mass, what we are concerned on finding. into total mass. So total mass is, guys, I think you can see the mass of one rectangle is there here. Can you see y delta x rho is the mass of one rectangle. So y delta x rho is the mass of one rectangle. So take the summation of all the rectangles from A to B. So if you add now y delta x rho is the mass of one of this. So you know there are many there are many rectangles. Yeah? So you take the addition from of all the rectangles from A to B. So that gives you the total mass. All right, guys. All right. So guys, next step, let's make x bar the subject. So when you make x bar the subject, we get here y, actually delta x, it's better if you can put it inside the bracket, y delta x rho times x divided by y delta x rho. Is that okay, guys? So I have my x bar equation. But actually, I hope you, so now we have come to a point where we got x bar subjected, but you guys know that there are, thousands or millions of rectangles here, right? So it's basically, it's not possible for us to, simply add this all, right? So basically, there is a special technique that we pull off here, and this is where we use the calculus. Okay, so look what's the next step that we do here. All right, guys. So the special technique that we pull off here is this. Now you guys know that we need to make this delta x as close to 0 as possible, right? So that was the whole goal from the beginning. Okay, so if you want to make, when delta x becomes as close to 0 as possible, so the special technique here is the summation, it becomes integral. So that's the special thing. The summation becomes integral. So over here, x bar equals, okay, guys, the summation turned into integral. So over here, y times x times rho, y times x times rho, guys. And the other thing is the delta x is becoming what becomes your dx. So this is the special technique you need to know here. Again, the summation becomes the integral sign, y, the delta x, let be there, the rho, y rho, and the delta x is what becomes the dx. Okay, so basically now you have an integration that's happening with respect to x. Okay, so this is what you need to know. This is the special technique that we use here. So x bar equals, guys, rho is a constant. You can take it out. Okay, so rho, because rho is a constant, and it does. The integration is happening with respect to x, right? So you can take the rho out, and you have here integration of xy with respect to x divided by rho times the integration of y with respect to x. So rho is a constant, it can cancel out. And you have your final equation, x bar equals integration of xy with respect to x divided by integration of y with respect to x. And your limits, by the way, the integration limits are a to b, right? Because the summation limits were a to b. So your integration limits will also be a to b. All right, guys. So this is the equation for x bar. And if you can input the y value, now who is the y value? Guys, over here, the y value is actually by y, you can, if you know the equation of the line here, basically you have a curve, the curve here, right? So if you know the equation of your curve, say y is equal to x square, something. So if you know the equation of y, you can substitute the y equation as x square, and you can perform the integration, and you can actually find the center of mass. All right, guys. So this is one main equation. So this is the main equation which you must know how to derive, as well as you should know how to directly use it as well. Okay, so now using the same technique, let's try to find y bar. All right, guys. So we found x bar. Now similarly, let's apply the same strategy to also find y bar. So to find y bar, it's again the same story. You multiply the equation we use is sigma mi equals total mass y bar into total mass. So total mass is sigma mi. Okay, so it's the same thing again. Okay, so all you got to do here is sigma, so mass into center of mass, mass for y times delta x times rho, and you multiply with the center of mass. Now we'll be multiplying with the center of mass y coordinate. So y coordinate is y over 2. All right, so mass into center of mass, that's done, equals y bar times total mass. So you add the mass y delta x rho. Okay, so y delta x rho. And you know the summation is from A to B. So the same exact story that we did before. So making y bar the subject gives you, so here you have y square over 2 rho times delta x over summation y rho delta x. I'm just rearranging slightly, okay? So guys, this is what we have. So once again, you can write this exact same statement as delta x limits to 0. The summation becomes integrals. Therefore, you can rewrite the equation y bar equals the integral sign a to b half y square or y square over 2 rho delta x becomes dx. Divide by the integration sign a to b y rho times delta x becomes dx. And once again, the rho is a constant which you can take out of the integral sign. So rho comes out and you get here half y square dx divided by the rho comes out y dx. So the rho cancels out. So y bar equals half integration. You can take the y square out or keep it in. So integration limits a to b divided by y dx. Integration limits a to b. So guys, these are the two special equations. Okay, so these are two special equations. You must be able to derive them also, and also you can, when they give you the opportunity, you can directly use it as well. So depending on the question, okay, so most of the time you'll be given to directly use the equation, but sometimes if it needs to be derived, then they will ask you to derive. Okay, so anyway, you need to know the derivation as well as you must know how to use these equations as well. So now I hope I have explained to you clearly how the equations are derived. So now let's see how to use them. Okay. All right. All right, guys. So let's practice with the sum here. So this is from exercise 5A, question number 1. They say find by integration the center of mass of the uniform triangular lamina enclosed by the lines y equals 6 minus 3x, x equals 0, and y equals 0. Okay, so let's quickly draw this particular line. So how does y equals 6 minus 3x look like? Y equals 6 minus 3x. So when you cut the x-axis, you set y to 0, 0 equals 6 minus 3x, and we get here x equals 6 divided by 3, x is 2, right? So you get here y equals 6 minus 0, and y is 6. So we have the two cutting points. X is 2. This is 0, 6. All right, guys. So now what's the, first of all, you need to find the enclosed region. So what's the enclosed region? Now I have drawn the line y equals 6 minus 3x. So the enclosed region, they say it's bounded, the center of mass of the uniform triangular lamina enclosed by the line y equals 6 minus 3x, x equals 0, that's the vertical line, y equals 0, that's the horizontal line. So guys, I hope you can see that it is this, right? So this is the area that we're talking about. So basically I have the I have a rectangular lamina here. So I am trying to find the center of mass of this rectangular lamina. Okay, so how do we find the center of mass of the rectangular lamina? We are going to use the find by integration, right? So which means we are going to use these two equations. Okay, so let's use the equation. X bar equals integration xy dx integration y dx. So guys, what are the limits here? And what are our a and b? So basically we are integrating with respect to x. So you need to use the x limit. So you can see here the x-axis. the area starts at the point 0 and ends at the point 2, right? So your integration limits should be from 0 to 2. All right, guys. So you can find the numerator integration separately, denominator integration separately, and get the answer. Okay, so you can do it separately. Or else you can do it together, right? So in some cases where the integration is quite complex, I recommend you to break it up and do it separately and get it together. Okay, so, but over here, I believe it's simple, okay, a little bit more of a simple one. So anyway, I'll do it separately. So the denominator, so how do we integrate here? X times, guys, we need to integrate xy with respect to x, but I need to get the formula for y, right? Because we need to input y in terms of x. So we know y is equal to 6 minus 3x. Can you see y is equal to 6 minus 3x? With respect to x, limits are 0 to 2. So let's integrate. 6 into x is 6x minus 3x square. So we still didn't integrate, we just expanded the bracket. Now let's perform the integration. I have here 6x square over 2 minus 3x cube over 3. And our limits are from 0 to 2. So guys, input the limits and get the answer. This is 6 over 2 is 3 into x square is 2 square. 3 and 3 cancels, x cube, that's 2 cube. Minus 0. When you substitute 0, the whole equation becomes a 0. So 3 into 2 square, that's 12 minus 8, right? So 12 minus 8, that's a 4. All right, guys, that's a 4. And then let's get the denominator as well. So denominator is y dx, right? Denominator integration is y dx. Limits are from 0 to 2. So y equation was 6 minus 3x. Agreed? Y equation was simply 6 minus 3x because we need to input in terms of x because our integration is happening with respect to x. All right, so integrate 6 integration is 6x, 3x integration is 3x square over 2. Input the limit from 0 to 2. So 6 into 2 minus 3 into 2 square over 2 minus the other limit 0. So this is 12 minus 6, which is 6, right? All right, so I have both the bounds, so time to substitute the values. So top value is 4, the bottom value is 6. 4 over 6, which gives us the x bar answer as 2 over 3. So this is your x bar answer using integration. All right, guys, can you see? Now, similarly, you have to find y bar.